This is a screencast in place of lecture for October 9th, 2019. In the screencast, I'm going to talk about optimization. I'll introduce with a little bit of advice or theory, and then go through some examples. So first, when you're finding absolute mins and maxes of a function on a closed interval AB, which is often a core piece of an optimization problem, mathematically speaking, the core of the calculation, what you need to do is find all the critical points, which are points at which the derivative is either 0 or not defined. Evaluate f at each of those critical points, and at the endpoints as well of the interval, f of a and f of b. And if you're looking for the max, then you take the biggest of all of those values. And if you're looking for the min, you take the smallest of all of those values. So if you have, for some reason, an interval that's not closed on both or one of the ends, you may not end up with a min or a max, an absolute min or an absolute max. For example, if we had a domain here that did not include the upper end, and so that's at B, then we wouldn't have absolute min for this problem. We also don't have an absolute max for this problem because you can get closer and closer to that empty hole, never reaching the height of the hole, but that hole, the height of that hole is sort of above everything around on the function. And just a reminder, you really don't need, if you're going to do this point comparison, all the critical points and the endpoints, you don't really need to do a first or second derivative test to determine whether you have mins or maxes, because the highest point had better be a max whether you test it or not. There's no way for it to be a local min, so there's no real reason to check that. Okay, so on to optimization per se. So given a scenario involving a choice of some number, and the difference here is when we were talking about absolute extremum, we were just getting a mathematical problem. Now we're going to give a scenario that has to be translated into a mathematical problem so that we can figure out a number to choose that solves the problem we're facing. So the first step I recommend is establishing an expectation based on your intuition into the problem, and use that later as a reality check on your answer. And if in the end your expectation doesn't agree with your calculated answer, then you've got to go back and fix one or the other, right? Maybe your expectation had some misconceptions underneath it, or maybe you miscalculated or defined your function poorly. So the next step is to translate the scenario into a mathematical problem so that you can do some calculus. I strongly recommend drawing some sketches, at least 3 of them, so that you can get a grip on what the extreme cases for the problem would be and what a central case would be. So in other words, like what would happen if your free variable that you're trying to optimize over is at one end of some natural interval in the problem or the other end, and somewhere in the middle. And then solve the mathematical problem to get an answer, the best value or the max of this function is f. And once you figured out that, translate it back into the language of the scenario that you're given and compare it to your expectation. And as I said, once you have an answer, you can compare it to the expectation, and if they don't match, you really should reconcile that, either by finding an error somewhere in your calculations or figuring out why your expectation is faulty. Okay, so throughout here there's some extra tips I want to throw in. Obviously you have to read the problem before you get started, and most students do that. One thing that I would recommend along the way is read the problem again after you've established an expectation, let's say, just to make sure that you got all the information correctly. When you're translating it into a mathematical problem, probably best to read it again. And as you're drawing sketches to get an idea of the extremes, make sure you get those extremes right one more time reading through it. And so on throughout. So basically, I have the impression that many students don't read the problem enough. I would expect that for any longer problem of these types, you should be reading the problem somewhere between 4 and 8, maybe 10 times, depending on how much information there is to extract from the problem. Okay, so here's our first clicker question and first example. So I have 10 meters of fence and I want a rectangular enclosure that's as small as possible for my goat, but it can't be narrower than my goat, and my goat is about 1/2 meter across. So how long and wide should I make the enclosure? So I'll let you stop the video right now and do some thinking, and then when you come back we can talk about the answer. Okay, so I trust that you've picked one of these, and not just randomly picked, but actually done some calculations and figured out what the best answer is. So, so what we're looking to do here is we're looking to find the min of the area as a function of the width, or you could have written as area as a function of the height, and I'm just putting it down for now. We'll go through it in a minute. The area is the width times 5 minus the width, and that's because we have 10 meters of fence, so that's how we end up with an expression for the height. And the interval in which width can vary is from 1/2 to 9/2, and that's because the limits are when you finally squish down narrow enough to squeeze my goat. Okay, so this is what the function looks like, but we have to chop it off at 1/2 and 9/2. And so just looking at this visually clearly, the lowest values are at the endpoints. So the answer to this problem is going to be L is 1/2 and W is 9/2. So let's go through just what the general structure of this problem is, and as I go through that, I'll give you the work behind the calculations in the previous example. So the previous optimization example is a very simple case of what we call a constrained optimization problem. That is, not only are we optimizing some quantity, but we're doing it subject to a constraint on some of the parameters. So first thing, we have an objective function, which is what we call the function that we're trying to maximize or minimize. And in this example, it's the area, which initially is a function of the length and the width. We don't know how the length and the width will relate, and if we had an infinite amount of fence to work with, there would be no reason to tie those two together. But we're given a limit, so we call that our constraint. And in this case, the constraint is that the perimeter can be no more than, or well, the problem should have stated that we have to use all the fence, because of course we could have used less than all 10 meters. So let's say we use all the fence, then the perimeter of it is going to be 2L plus 2W, and that's equal to 10. This establishes a relationship between L and W, and that's what we call the constraint. And it lets us solve for one of these variables in terms of the other. And so I've chosen sort of arbitrarily, and it doesn't really matter, you get the same problem either way. I've chosen to solve for L, so the length will have to be 5 minus W. And I substitute that value of L into the equation. That's where I got my A of W is 5 minus W times W. And now often we're going to end up with constraints that are hidden, right? There's nothing about this function itself that says W should be limited in any way. It's just a quadratic. But the problem, the statement of the problem in the physical scenario suggests that W should always be bigger than 0 and less than 5. Bigger than 0 because it doesn't make sense to have, oh, no, those are actually not the ones I wanted. I wanted a more restrictive one, so let me fix that. So we want W to be greater than 1/2 a meter, and that's because of the width of my goat. But we also want L to be less than, or sorry, greater than 1/2. And when I put that over here, I want 5 minus W, and if I use this L minus 5W relationship, to be greater than 1/2. And that gives us that W has to be less than 5 minus 1/2, which is where that 9/2 came from. Okay, so I want W to be between 1/2 and 9/2. Okay, so that's a constrained, the general structure of a constrained optimization problem. We have an objective function we're trying to find a max or min of. We have a constraint that relates two variables, both of which appear in our objective function. We use that constraint to reduce it down to a one variable function, and we know how to do calculus on one variable functions. Okay, so let's do a little bit more of an involved example. Actually, I'll take a pause here and start a new screencast just so we don't get videos that are too long.